W13 gratings. So we've done Young's double slits and we've done the single slit pattern. So if the double slits produces several fringes, many fringes in fact, what happens when you have many slits? So the thing that we're making is called a diffraction grating, and it has many slits. Typically the ones we use in the lab have either 80 lines per millimetre, which means that each slit is an 80th of a millimetre, and if we work that out as a decimal, it's 0.125 millimetres. The other typical one is 300 lines per millimetre, much finer grating, so each slit is a 300th of a millimetre, and that comes to 0.0033 millimetres, so tiny slits. Now what we have therefore is something like this. So each of these points in this diagram represents one of the slits, and they are so tiny that the waves going through that slit diffract almost completely through 180 degrees from side to side. Obviously they can't diffract any further than that because they'd be going backwards, but you get these actually hemispherical wavefronts, and there are many of them. So the light can go through. I'll just think about these three slits here, and the tips of the first set of wavefronts form a line, and so does the next one, and the next one, and the next one, and so on. So we've got a whole load of wavefronts marching off in that direction, and they will arrive at the screen straight ahead to form a bright point and the 0th order fringe. But if we look here, we've got the first wavefront from this source and the second wavefront from this source. I've drawn a line between them. If we draw the next one out, this touches the second wavefront from this source and the third one from that source, and so on. I can see three of them, so this one, and this one also form a line. If I continue that, I've got wavefronts heading off in this direction, again all in phase, and that will form the n equals 1, the first order fringe. In between these two directions, the wavefronts will end up arriving in many different phases, so they won't add up to anything significant. So you don't get any light off in these directions, only in the directions where the arrows are. If I look a bit further, the mauve line I've drawn connects the first wavefront of this one and the third wavefront of that one, and here we've got the same again. So off in that direction they will all arrive at the screen in phase as well, so we'll get a third bright spot, and this will be the n equals 2 fringe. So there's our 3 fringes. Now we have a 3mm laser beam. It's not very big, but on this scale, if I have a 80 line per millimetre diffraction grating, that means the light from the laser will be going through about 200 slits, and if I've got a 300 line per millimetre grating, it'll be going through about 1,000 slits. So although a very tiny amount of light goes through each slit, I've got many of them adding together at the distant screen. So we do get these very distinct bright spots at just those locations and nowhere in between. Thinking about it as a sort of three-dimensional situation, we've got beams travelling off in different directions. If we're doing it in a room, in fact, these ones would end up hitting the side wall rather than the screen straight ahead. But as you can see, they can't go backwards. There's a limit to how far round they can go because of this, where the diffraction grating actually is in relation to the laser beam. So this is the diagram from the book. We can see the rays going off, heading off to their first order fringe. We zoom in on this little bit here, just the distance between two of the slits. We've got a triangle, and here it is blown up. So we've got an angle theta between the diffraction grating and the wavefronts heading off to the n=1 fringe. So for n=1, qy, this distance here, is one wavelength. So sine theta is lambda qy over d, the distance between the slits. For the nth order beam, that distance qy will be a multiple of a wavelength. So for the second order fringe, you'll fit in 2 wavelengths there. For the third order fringe, you'll fit in 3 wavelengths, and so on. So we get sine theta is n lambda, n being the order of the beam, n lambda over d. So we've got this equation, n lambda equals d sine theta. So just to recap, n stands for the beam number, the order of the fringe, starting with 0 in the middle. Lambda is the wavelength of the light we're using. D is the distance between 2 slits. So if typically you're given the slits per millimetre, so you need to convert it into millimetres per slit, that's D. And theta is the angle to the nth beam. Okay. Here's a picture of a bright light source being viewed through a diffraction grating, so you can see the actual image of the light source straight ahead, and to each side we can see the nth order, in this case the first order set of fringes. And because in this equation we've got n=1, so we're looking at the first order fringe, d is constant because it's obviously through one particular grating. So in the equation, as lambda increases, sine theta increases. So as you can see, the larger the wavelength, as we go towards red, the further out it is, the bigger theta is. And what happens when you get 2 gratings crossed over? You get this rather nice pattern. So it's diffracted not only horizontally, but also vertically as well. Cross gratings used to be used quite a lot by photographers for special effects before the days of Photoshop.